Hello everyone, welcome to another episode of Shake Hand with Life YouTube channel. I am Narendra Sharma. In this video, we will study the two-way Anova for testing a hypothesis with repeated values. With an example, it implies when an experiment is repeated and there are two different factors that could impact the null hypothesis. So we will understand how to calculate the F ratio and F limit and test the null hypothesis by comparing the F ratio against F limit for each factor. Right. So make sure that you have subscribed Shake Hand with Life YouTube channel and hit the bell to get the notifications of my latest video lectures. Now let's begin it. Here is an experiment is given for the amount of blood pressure reduction in mm of mercury by three drugs X, Y and Z on three groups of people A, B and C, and the amount of BP reduced by X, Y and Z for first group, which is A, are 14-15, 10-9 and 11-11. Right. So the experiment is repeated twice for each drug, right? And the amount of BP reduced by X, Y and Z for second group, which is B, it is 12 and 11, 7 and 8, 10 and 11, right? Okay, this is the amount of BP reduced by X, Y and Z for second group. Now the amount of BP reduced by X, Y and Z for third group, it is 10, 11, 11 and 11, 8 and 7, right? So these are the observations which we have collected from the experiment. Now the outcome is effectiveness of three drugs X, Y and Z in reducing blood pressure. This is our outcome. Now how many factors we have? We have two different factors. The first one is different types of drugs. So we have three types of drug here. This is the first factor. Now second factor is the drugs are tested on different groups of people. So the second factor or the second category which could affect the result is different groups of people, right? So we have two different factors that could affect the result. Now what is the null hypothesis if these two factors not affect the outcome or the result? In that case, BP reduced by X, Y and Z in same amount, right? And at which significance, what significant level we are going to test the null hypothesis? It is 5%. Now from this experiment, what we want to find out? First we want to find out, do the drugs act differently? This is our first question. The second one is, are the different groups of people affected differently? So the second question is this. So how the people react to the drugs, or they are significantly affected by the drugs. And the third one is the interaction term significant? So the interaction means interaction of these three drugs and the three groups of people. So is the interaction term is significant? This we also find out. Now to solve this problem, we first state the null and alternative hypothesis. So here the null hypothesis is amount of BP reduced by three drugs is equal. So this implies that the mean amount of BP reduced by X drug and the mean amount of BP reduced by the drug Y and the mean amount of BP reduced by the drug Z, all three are equal. This implies that there is no effect of two factors like the types of drugs and the group of people in reducing blood pressure. Okay, so this is our null hypothesis. And what is our alternative hypothesis? The alternative hypothesis is assumed as amount of BP reduced by three drugs is different. So it implies there is a significant effect of two factors like types of drugs and the groups of people. So these factors, the drug factor and the group of people. These two categories significantly affect the results or the outcome, which is the effectiveness of the three drugs in reducing the blood pressure. Okay. Now we calculate different terms. To calculate the F ratio for two-way ANOVA when we have repeated values or the repeated experiment. Right. So in step number 1, we calculate the correction factor first. So here we use the method of use the coding method, right? Okay. So for coding method, we need to calculate the correction factor. So how many elements we have or the data values we have? We have 18 data values. So here we have 18 data values. So 6 are here, 6 are here, 12 and 6 are here. 18 data values we have. Okay. And the total of all these data values we have 187. Therefore the correction factor is t square by n. And the t square, t is 187. So 187 square of 187 divided by 18, we have 1942.72. Right. So this is our correction factor. Now okay. Now in step number 2, we calculate the sum of square for total variation. And how do we calculate that? First we square the each element and then add all the squares, right? So the square of 14, square of 15, square of 12 and so on. Square each element. Right. So we have square of each element and then we add all the squares. And the sum of square of each element we get 2019 if we solve this. And then subtract the correction factor. So the correction factor is square of 187 divided by 18. So here we have subtracted this. So when we solve this we get 1942.72. So here the 1942.72 and we get 76.28 as sum of squares for total variation, right? Okay. So this is our sum of square for total variation, which is 76.28. Now we calculate the sum of squares for variation between the columns. So here we have 3 columns. Column number 1 is for X, column number 2 is for Y, column number 3 is for Z. So we have 3 columns, or we can say that the sum of squares for variation between the drugs, right? So between the drugs. So first we find the total of each column. So the total of first column is 73, total of second column is 56, total of third column is 58. Now square the total of each column and then divide the number of elements in each column. So the total of first column is 73. So here we have square of 73 and then divide it by 6 because we have 6 number of elements in first column. Similarly 56 square divide by 6, and for third column it is 58 square divide by 6. And subtract the correction factor. Again subtract the correction factor, which is 187 square divided by 18. So from this we get 888.16. From this we get 522.66, and from this we get 560.67, right? And solve this. When we solve this we get 1942.72. Now add all these 3 numbers, we get 1971.49, and the value of correction factor is 1942.72. and when we subtract the correction factor from this value we get 28.77. So this is our sum of squares for variation between the columns. So we calculate the correction factor first, then we calculate the sum of square for total variation, which is 76.28. Then in third, we calculate the sum of squares for variation between the columns, right? So, or between the drugs. Now in step number 4, we calculate the sum of squares for variation between the rows, or between the people, or between the groups, right? So to calculate, first we find the total of each row or each group, right? So the first group is A, or the first row is A, the second row is B, or the second group is B, and the third is group C, or the third row, right? So first find the total of first group, which is 70. Sum of 14, 10, 11, 15, 9 and 11, we get 70. Similarly, for group B, the total is 59. For group C, total is 58. Now square each total of each row, and then subtract the number of elements. So for row number 1, which is, or for group A, it is square of 70 divided by number of elements, which is 6. Now for group B, it is 59 square divided by 6, and for group C, it is square of 58 divided by 6, right? And then again subtract the correction factor, which is square of 187 divided by 18, right? Now from this, square of 70 divided by 6, we get 816.67. Now square of 59 divided by 6, we get 580.16, and then square of 58 divided by 6, we get 560.67, right? And the correction factor, the value of correction factor is, when we solve this, we get 1942.72. Now adding all these three values, we get 1957.50, and the correction factor is 1942.72, and when we subtract the correction factor from this value, we get 14.78, right? Now in step number 5, we calculate the sum of square within the samples. Okay. Step number 5, sum of squares for variation within the samples. So to calculate that sum of squares for variation within the samples, we repeat the experiment twice, right? For X, we take two values, so 14 and 15. First we calculate the mean of these two values. So mean of these two values is 14.5. Now subtract 14.5 from 14, and then subtract the 14.5 from 15, and then square it, right? Square it. So here we have the square, right? So similarly we do for 10 and 9 in group A. So here we have 10 minus 9.5 square and 9 minus 9.5 square. Because the mean of 10 and 9, we have 9.5. Similarly, the mean of 11 and 11, we have 11. Therefore, 11 minus 11 square and 11 minus 11 square again. Now, the mean of 12 and 11, we have 11.5. Therefore, 12 minus 11.5 square, and then again 11 minus 11.5 square. Now, for this 7 and 8, so the mean is 7.5. Therefore, 7 minus 7.5 square, and then 8 minus 7.5 square, right? Now for 10 and 11, we have 10.5. The mean value for 10 and 11 is 10.5. So this is 10 minus 10.5 square, and then again 11 minus 10.5 square, right? Now for C it is 10 and 11. Mean of 10 and 11, again 10 minus 10.5, because mean of 10 and 11 is 10.5. So here we have 10 minus 10.5 square, then again 11 minus 10.5 square, right? Now we have 11 and 11. So the mean of 11 and 11, we have 11. So 11 minus 11 square, then again 11 minus 11 square. Now the mean of 8 and 7. So mean of 8 and 7 is 7.5. Therefore, it is 8 minus 7.5 square, and then again 7 minus 7.5 square. So from this we get 0.25, from this we get 0.25, from this we get 0.25, 0.5 square, and from this we get 0.5 square, again we get 0.5 square. From this we get 0, so 0, we get 0 here, then again we get 0 here from this, right? And 0.25 from this, so I take different color, so here I just take different color, so identify that. Then from this we get 0.25, then again from this we get 0.25, from this we get 0.25, right? So 11 minus, so here is 10 minus 10.5 square, we get 0.25, from this we get 0.25, from this we get 0.25 again, from this we get 0.25 again, and from this again we get 0.25. So from this we get 0, so here 0, again we get 0. So from this 8 minus 7.5 square we get 0.25, and 7 minus 7.5 square we get 0.25. Okay, now we add all these values. So when we add all these values, so 0.25, 0.25, 0.25, 0.25 equal to 1, right? And 0.25, 0.25, 0.25, 0.25 equal to 1 again. So 1 plus 1 equal to 2, and so here we have 0.25, 0.25, 0.25, 0.25 equal to 1, and so we get 2 plus 1 equal to 3, right? And we have 0.25, 0.25, so this is 3.5, so we have 3.5, right? Now in step number 6 we calculate the sum of squares for interaction variation. So interaction variation, how do we calculate the interaction variation? In step number 6 we calculate the sum of square for interaction variation. So sum of square for total variation is 76.28, which is here, and then subtract the sum of squares for variation between the columns, which is 28.77, and then 14.78, which is here, and then sum of squares for variation within the samples, which is 3.5. So 76.28 and minus sum of all these three. This is sum of square for variation between the columns, and this is the sum of square variation between the rows, and this is sum of square for variation within the samples, right? So sum of all these three we get 47.05. So when we subtract 47.05 from 76.28 we get 29.23. So this is the sum of square for interaction variation, right? Now we assume the null hypothesis as the three drugs, the amount of BP reduced by three drugs is equal, and the alternative hypothesis is assumed as the amount of BP reduced by three drugs is different, right? Now here is our experiment. So this is our experiment, right? And for this experiment we calculated the sum of squares for total variation 76.28, sum of squares for variation between the columns X, Y and Z we have 28.77, and sum of squares for variation between the rows A, B and C we have 14.78, sum of squares for variation within the samples 3.50. So within the samples, this we have calculated 3.56. Now the sum of square for interaction variation is 29.23. So interaction of x, y is z and a, b and c. Number of elements we have 18, number of columns we have 3, and number of rows we have 3, right? Now we prepared the two-way Anova table and calculate the F ratio. So here we have the source of variation, then here we have in second column sum of squares. So sum of squares for variation between the columns we have 28.77. Sum of squares for variation between the rows or between the people or between the group of people we have 14.78. Sum of squares for variation for interaction variation we have 29.23, and sum of squares for variation within the samples or error is 3.50, and the sum of square for total variation or the sum of squares for total variation we have 76.28, right? Now we calculate the degrees of freedom, corresponding degrees of freedom. So how many columns we have? We have 3 columns, therefore 3 minus 1, the degrees of freedom for sum of squares for variation between the columns is 2, and the sum of squares for variation between the rows is also 2 because we have total number of rows 3. Now the sum of squares for variation for interaction variation between column and rows, because the number of columns we have 2, number of rows we have 2, therefore 2 into 2, 4. Therefore 4 is the degrees of freedom corresponding to the sum of squares for interaction variation. Now the sum of the degrees of freedom corresponding to the sum of squares variation within samples. So we just calculate the mean for each 2 cell, right? For the sample, for the group of people, for each group. So for these 2 cells we have one mean, and again then we have one mean also, and then for these 2 cells again we have one mean. So therefore we have total 3 means for this row, for group of people A. Similarly we have 3 means for the group of people B, and then I just clear it again and just make it clear to you. So we have mean for these 2 values, mean for these 2 values, and one mean for these 2 values. So how many means for this group of people A? We have 3 mean, and then again we have one mean for these 2 values, again we have one mean for these 2 values, and we have 3 mean for group of people B. Similarly we have 3 means for group of people C, right? So how many means we have? We have total 9 means. Therefore the degrees of freedom corresponding to the sum of squares variation within the samples is 18 minus 9. So 18 is total number of elements minus number of means we have 9 means. So 18 minus 9, we have 9 degrees of freedom, right? And finally the degrees of freedom corresponding to the total variation. So how many elements we have? We have total 18 elements. So the degree of freedom is 18 minus 1 equal to 17. So these are the degrees of freedom in column number 3. Now we calculate the mean square for the between the mean square for variation between the columns. So here we have 28.77 divided by 2, the degrees of freedom. So 28.77 divided by 2, we get 14.385. Now the mean square for variation between the rows, so it is the sum of square for variation, which is 14.78 divided by corresponding degrees of freedom, which is 2. So 14.78 divided by 2, we get 7.390. Now the mean square for variation between the variation for interaction variation, so it is sum of square for interaction variation, which is 29.23, and the degrees of freedom is 4. So the mean square for interaction variation is 29.23 divided by 4, we get 7.308, right? Now the mean square for variation within the samples, right? So it is the 3.50 sum of squares for variation within samples divided by the corresponding degrees of freedom, which is 9. So 9, 3.50 divided by 9, we get 0.389. Now we calculate the F ratio. So for F ratio in numerator, F ratio for the between the columns or between the drugs, the category of drugs. So it is the mean square for variation, which is 14.385 divided by the mean square for variation within the samples or error, which is 0.389, right, in denominator. So we get 36.9. Now the F ratio for the between the rows, so F ratio corresponding to the rows or between the people or between the groups of people. So we have 7.390 in numerator, right, and divided by the mean square for variation within samples. So it is 0.389 divided by 0.389 in denominator. So we get 19.0. And the F ratio corresponding to the interaction variation, so it is 7.308 in numerator and 0.389 in numerator, right? So when we divide 7.308 by 0.389, we get 18.79. So here we have three F ratios corresponding to the between the columns, interaction between the columns, variation between the columns, and the variation between the rows, and the interaction variation, right? So here we have three F ratios. Now we compare these three F ratios with the corresponding F limit at 5% significance level. And how do we calculate the F limit? We'll see in next slide. Now we'll calculate the F limit at 5% significance level. So here we have F29, the F limit corresponding to the variation between the drugs, right? And then we have F29, the F limit corresponding to the variation between the group of people. And then we have the F limit corresponding to the interaction variation. So F29 is equal to 4.26. Therefore again we have F29 is 4.26 and F49 we have 3.63. So how do we calculate all these F limit? We'll see here. So here is the critical values of F distribution at 5% significance level. So our first limit is F29. So F29, and again we have F29, and third is F49. So for F29, 2 is in the numerator. So 2 is in the numerator and 9 is in the denominator. So F29, 2 up to 9. So here we have 9. So this is our F limit for F29, 4.26, right? And the next one is F49. So F4 is in the numerator. So here is in the numerator, and 9. So here we have the 9. This is 3.63. F49. So 3.63 is corresponding to F49, right? So this way we can calculate the F limits corresponding to the first factor, which is the drug, so variation between the drugs, and the second factor is variation between the group of people, and the third factor is interaction between the drug and group of people. So here we have calculated the three F limits. Now in next slide we'll compare the F ratio and F limits and conclude about the hypothesis, what we our null hypothesis. Okay, now we test the null hypothesis by comparing the F ratio and F limit for all three factors. The first factor is the effect of drug, and the second factor is the effect of how the people are affected by three drugs, and the interaction between the drugs and the group of people, right? Okay, now just remind the null and alternative hypothesis. So the null hypothesis H0 is the amount of BP reduced by three drugs is equal, right? And the alternative hypothesis is amount of BP reduced by three drugs is different. That means the people affected differently from three drugs, right? Okay, now the first factor, consider the first factor, which is the effect of three drugs, right? So here we have the F ratio is 36.9 and F limit is 4.26, and clearly the F ratio is much greater than F limit, and therefore for this case the H0 or the null hypothesis need to be rejected. Okay, so here we reject the null hypothesis for the first case. Now for second case, or for second factor, which is the group of people, how the group of people affected by three drugs, right? So for this case the F ratio is 19 and F limit is 4.26, and clearly again the F ratio is much greater than F limit, and again we reject the null hypothesis for this case. So here the null hypothesis again rejected for the group of people for the second factor. Now the third factor is interaction of the drug and the group of people. So here the F ratio is 18.79 and F limit is 3.63. So again we find that the F ratio is much greater than F limit. So we again reject the null hypothesis. Now we can draw the conclusion for all these three factors. Now first is all three F ratios are significant of 5% for all three cases, because we test the null hypothesis at 5% significance level, and therefore all three F ratios are significant of 5%, right? Now the null hypothesis is rejected in all three cases, and it implies, and we see that we already seen that all three F ratios are much greater than F limit, and for all three cases the null hypothesis is rejected. So the conclusion we drawn here is the first one is the drugs act differently, and this implies that the amount of BP reduced by three drugs is different. So the first drug, which is X, affect the person differently, and the amount of BP reduced by the drug Y is different, and the amount of BP reduced by the drug Z is different. Okay, now the second one is different groups of people are affected differently by three drugs, and this implies the amount of BP reduced is different for all three groups. This implies the people in three groups react differently for all three drugs X, Y and Z. Okay, now the third case is interaction term. So the interaction term, we already seen that the interaction case the F ratio is much greater than F limit, and we see that the F ratio is greater than F limit, and in that case H0 is already rejected, or the null hypothesis is already rejected. So clearly if the interaction factor is significant, then automatically, or we can say that obviously, it is very obvious that the first case, the effect of drug and how the people are affected, these two factors also significant of 5%, right? So this is the way how do we conclude about a problem, or how do we conclude about the null hypothesis, or how do we test the null hypothesis for two-way ANOVA when we test the null hypothesis for two factors like the drugs and the group of people. And that's it. If you have any question or suggestions, then please do write your feedback in the comment box below. Hit the like button and share this video with your friends and colleagues. Switch to Shake Hand with Life YouTube channel for more videos. Subscribe the channel and hit the bell to get the notifications of my latest video lectures. Visit on shakehandwithlife.in to download the course notes and ebooks in PDF. See you soon in my next video.